Welcome everyone to Algebra 1, Section 2.6, Literal Equations. So literal equations are equations with multiple variables. Now, because of the fact that it has multiple variables, solving them looks a little bit differently, or looks a little bit different between the two of a literal equation and our normal equations we've had up until this point. So let's look here at these two equations on the left and right. So here on the left we have 2x minus 5 equals 13, an equation we would have seen earlier this unit, whereas on the right we have ax minus b equals c. Obviously different compared to what we've been used to with a lot of variables there. Now both have two things multiplying together, subtracting something, and equaling something on the other side. So they have the same overall structure. We have a product, subtraction, and equaling one thing. So actually the how we solve them, there's a lot of overlap. So here if we were to solve this one, our first step would be to undo the subtraction. If we were to solve for x, it says specifically, undo the subtraction by adding 5 to both sides. And so we end up getting negative 5 plus 5 is 0, and so we have 2x plus 0, which is just 2x. And on the right side, we can combine 13 and 5 and get 18. Now if I pause and go over here for the first step, I would once again say x is being multiplied and subtracted, and I undo the subtraction first by adding. This time instead of adding 5, I'm going to be adding b. And negative b plus b is 0, and I don't have to write ax plus 0, I can just write ax. And just like I did over here when I added 5 on one side, I had to add it to the other, so I have to add b to the other side. Now over here in this equation on the left, we were able to combine 13 and 5 and get 18. Here on the right, I can't combine b and c, and so I'm just going to put b plus c or c plus b. I'm not going to be terribly concerned about the order right now, as long as you have both there, and they're both positive in this scenario. I typically will default to putting them alphabetically though. Now our next step over here would be to undo the multiplication of 2 with x, and so we divide by 2, and so 2 and 2 reduce, and we get x, or 1x, and then we divide by 2 on the other side as well and get 9. And that's our answer because x is by itself. On this equation on the right here, we also have to undo multiplication with x, and the multiplication we're undoing is the multiplication of a. So just like over here we divided by 2 to undo the multiplication of 2, we'll divide by a to undo the multiplication of a. And just like over here, how 2 and 2 reduce to 1 because 2 divided by itself is 1, a divided by itself is also 1. And so we get 1x or x. Now on the other side, we also have to divide by a, just as over here we had to divide by 2. And notice I've divided everything by it. You can either choose to put each one individually over a, or the entire thing over a. They are the exact same thing, so don't lose sight of that. So some of us might benefit from doing it individually. That way we remember each one's over a. But whichever one you do, I'm not going to be terribly concerned about. Now, over on the left, we could do 18 divided by 2 and call it 9. We don't know what b divided by a is, so we just write b over a. We don't know what c over a is, so we just write c over a, and we're still adding them. And so we end up just getting x equals b over a plus c over a. And once again, you could have combined them into one fraction, where we call it x equals b plus c over a, and it's the exact same thing. Now, just like over here on the left, x is by itself, and there's nothing more we can do on the right. X is by itself here, and there's nothing more we can do over there math-wise. And so we're actually done. And that can be really weird for a lot of us because it looks like it's not done. There's still a lot there compared to this equation over here on the left. But yet, x is by itself. We solved for what we wanted to, and we did all the math we could. So identify similarities and differences between the two equations. So one similarity would be that both used the same steps to undo operations. Both of them went in the same order, where we undid the subtraction first by adding, and then both undid the division or the multiplication by dividing. So that was all the same. Whereas a difference is that the literal equation, or the equation on the right with more variables, the literal equation doesn't simplify nicely. We didn't just get like one number or one variable on that side. So it doesn't simplify nicely. And that'll often be the case with these literal equations where we realize, well, that doesn't simplify very well, even when we solve. So let's go ahead and practice here. These are some one-step problems. So whenever we have a literal equation, we're given multiple variables, as we mentioned, and then we're told specifically to what variable to solve for. So you have to pay very close attention to that. So here we're solving for w. And so we ask ourselves a question, what's happening to w? W is being multiplied by L. How do we undo the multiplication? We divide by L. And L divided by L is 1, and we get W. And if we divide one side by L, we have to divide the other side. And then we ask ourselves a question, do I know what A divided by L is? And the answer is, I sure don't. So I'm just going to write A divided by L. And W is by itself. That's all the math we can do, so we're done. So notice we're really asking ourselves the same questions I encourage us to ask for our other equations of what's happening to the variable, how do we undo it, and going through the process there. So on number 2 here, A equals BH. This time we're solving for H. So to undo the multiplication of H, so what's happening to the variable, it's being multiplied by B. To undo the multiplication of B, we divide by B. B divided by itself is 1, and we get 1H or H. Divide the other side by B, and we do not know what A divided by B is, so we leave it as A over B. Now I do want to note on 1 and 2, these are using capital A's. That's because these are actually formulas for area. This is area equals length times width, and this is area equals base times height. True for quadrilaterals, or many quadrilaterals, or I should say all regular quadrilaterals. I will define what that means in geometry another year. But regardless, so they're using capital A, so that is specific here. If you were to write a lowercase a on this one, I wouldn't necessarily count it wrong, unless there were both lowercase and capital A's. But here, we just want to typically leave it as capital A if we remember to. On number 3, D equals RT, solving for T. So to undo these being multiplied, to undo the multiplication, we divide by R, and we get just T, or 1T. Divide the other side by R, and we get D over R. On number 4 here, we have capital I is equal to PRT, and so we're supposed to solve for T. So T is being multiplied by both P and R, so to undo that, we'll divide by both P and R. And P divided by itself is 1, R divided by itself is 1, and we're left with 1T, or just T. Now if we divided one side by both P and R, we have to divide the other side by the exact same things. And I don't know what I divided by PR is, so I just write I over PR. This is basically kind of like lazy math, to where we start something, but we essentially don't finish because we can't. Let's look at number 5 here. V equals LWH. We're supposed to solve for H. So H is being multiplied by L and W, so we undo that by dividing by L and W, and we end up getting just H. We divide the other side by the exact same things, and we end up getting V over LW equals H. Number 6, this one we're actually going to skip, and the reason why is we're supposed to solve for R. And R is being squared, and we have not learned how to solve those yet, so we're going to just skip that one. Number 7 here, M equals C minus S, and we're supposed to solve for C. So C is being subtracted by S. We undo that by adding S, and we end up getting C plus 0, or C. So add S to the other side. I don't know what M plus S is, so I just rewrite M plus S. C is by itself, and we're done. On number 8 here, D equals M over V, and we're supposed to solve for M. M is being divided by V, so how we undo that is by multiplying by V over 1, or just V. The V's reduce, and we get 1 times M, or M. Multiply the other side by V, or V over 1, and you get V times D, or D times V. Once again, I'm not going to be picky about the order you have these variables in, although I'm going to default to doing it alphabetically. Let's move on to our next page here. Multi-step problems, okay? So remember, some helpful hints here. We're going to think backwards, so not PEMDAS, but rather we're doing SADMEP, just like we have been for our other equations. Remove fractions by multiplying by their reciprocal, aka when fractions are multiplying with things, that's when we multiply by their reciprocal. If they're adding with things or subtracting with things, we do not do that. And then last step is usually to divide by whatever's next to your variable, usually because there are problems like we just had, for example, where we didn't divide, we multiplied because it was being divided. But the key thing here is really to remember SADMAP and the same steps you would if it was a problem with numbers rather than a problem with variables. Number 9 here, a equals 1/2 b times h. And we're supposed to solve for h here. So h is being multiplied by both 1/2 and b. Now, typically we divide to undo multiplication. So we divide by 1/2 b. However, that gets really messy and we don't like to divide by fractions. So instead I have to multiply by the reciprocal of 1/2, but I don't need to multiply by the reciprocal of b. So what I'm going to do is I'm just going to do this part by part, and this is why it becomes a multi-step problem. I'm going to deal with one of these, and then I'll deal with the other. Typically, I prefer dealing with a fraction first here, because the fractions that we're going to be using will work out okay to where once we deal with a fraction, we'll no longer have a fraction. That's because it's 1 over a number. So when we multiply by the reciprocal, 2 over 1, the 2's reduce, and I get b times h. And the other side, I multiply by 2 or 2 over 1, and I get 2 times a. And so that fraction worked out quite nicely here when we undid it to where we didn't have any more fractions now. And so now if I divide by b to undo the multiplication of h, because h is being multiplied with b, we divide it on both sides. And once again, you could choose to put this over each individually. But since it's already just one term there, they're not adding or subtracting, we just do it over the whole thing. If there was a plus sign, then once again feel free to put them each individually over b, or a minus sign as well. So 2a divided by b, we don't know that, so we just write it, and we get h. And now we solved for h. If you wanted to divide by b first, you certainly could. You would end up getting the same result. Number 10 here, v equals 1/3 b times h. We're supposed to solve for this capital B here. And so I'm going to say my b is being multiplied by h and 1/3. I can't undo them well at the same time because dividing by 1/3 h is messy because of the fraction. So I'm going to undo the fraction first here. You could undo the h first as well if you'd like. Undoing the fraction, we multiply by the reciprocal, which is 3 over 1. The 3's reduce, and I get capital B times h equals, multiplying the other side by 3, 3v. Now to get b by itself, I divide by h to undo the multiplication, and I get b. On the other side, divide by h, and I get, well, can't really do anything to simplify that. So I have 3v over h equals b as my answer. Number 11 here, k equals mv squared over 2. Now, even though this one has a squared here, we're actually not going to have to undo that one because we're not solving for v. In the previous problem, number 6 that we crossed out, that was the variable we were solving for was what was being squared. So here, m is being multiplied and divided. You certainly could undo either one first, but it's typically easier if you undo the division first, similar to how it is typically easier in 9 and 10 to undo the fraction first. So I multiply by 2 or 2 over 1. The 2's reduce, and I get 2k equals mv squared. Now my m is being multiplied by v squared, so I can divide by v squared. And I end up getting v squared divided by itself is just 1. Anything divided by itself other than 0 is 1. And on the left, I don't know what 2k over v squared is, so I'm just going to write 2k over v squared. And my m is by itself, and I did all the math I can, so I'm done with that problem. Now, I do want to note you could solve this one a slightly alternative way where you basically just combine the orange and blue steps here. So if I were just to restart this problem and just rewrite it, what you could do to combine those two is you could say, I'm going to multiply by 2 on the top to undo this 2 over here. And I'm going to multiply by v squared on the bottom to undo or reduce with that v squared. And now we're left with m. And I would do the same thing to the other side, 2 over v squared. Put k over 1, and I multiply straight across. Since I can't cross-reduce, I have 2 times k is 2k. V squared times 1 is v squared. And we end up with the exact same answer we ended up with over here in the blue, just doing it in one step. So that's also an option available to you, and that's only available to you here because m is multiplying with v squared, and so we can undo that with dividing, aka putting on the bottom of a fraction. Whereas if it was m adding or subtracting, didn't mean to tap that, adding or subtracting with v squared, it would not work to do that, because then we'd be undoing subtraction or addition with division, and that's not what undoes addition, subtraction. Number 12 here, we're supposed to solve for b. So here's an example of what we can't do. We cannot do d over c because we're not multiplying with c. So instead, I will just undo here the addition and division. I'll just undo the division first, which is d over 1. You have to undo the division first in this case, similar to how if I had like 5 equals x plus 2 over 3, I'd have to undo the division first as well, because remember, this is secretly x over 3 and 2 over 3. So here I undo the multiplication of d, or I undo the division of d by multiplying by d. Those reduce to 1, and I get b plus c. On the right-hand side, I multiply by d, and I could either call it dA or AD, which I will to keep it alphabetical. Now to undo the addition of c, I'm going to subtract c. And I don't know what AD minus c is, but I'm just going to write AD minus c and say that's equal to b and call it a day, because I got my b by itself, and I did all the math I could. Number 13, P equals 2L plus 2 width, formula for a perimeter of a rectangle. And we're supposed to solve for W here. So W is being multiplied and added. And we undo the addition first, so we'll subtract by 2L, that entire thing. And 2L minus itself is 0. Subtract the other side by 2L, and I don't know what P minus 2L is because those aren't common terms. They don't have the same variable. They aren't like terms, I should say. So we have P minus 2L is equal to 2W. And now I undo the multiplication of 2 by dividing by 2. And you can either divide the whole thing by 2, or this is where it can come in handy to divide each one individually by 2 when they're adding or subtracting. Because P over 2 I don't know, but I can do something here, where I can reduce those 2's and make this minus L, or L over 1. And on the right-hand side, I get just W. So we end up getting P over 2 minus L equals W. And if you had written it like this, where you just kept it over 1 to mimic this in the light blue, I'll just rewrite in the light blue here to give a good start on where we're at. If I had instead divided the whole thing by 2, it would look like this. But there's still something I can divide there, so I would want to separate these out like I did here, so I could reduce. Number 14, ax plus by equals c. And we're supposed to solve for y. So y is being multiplied by b and added with ax. I will undo the addition first by subtracting by ax. Ax minus itself is 0, and I get by on the left. Subtract ax on the other side. I'm going to do c minus ax. And here, it doesn't matter whether you put negative ax or c first. Here I happen to default to putting ax second here because we're subtracting it rather than writing negative ax plus c off the bat. But once again, either way is fine as long as we keep the ax negative like it is and the c positive like it is. Now we have to undo the multiplication of b, and we're going to undo the multiplication of b by dividing by b to absolutely everything. Now, here on this problem, the reason I wanted to specify that I divided individually by 2 is because we were able to reduce this 2 and this 2. Here, if I divide individually by b, I can't reduce either of those. So on this problem, I'm perfectly fine with you doing this, where you call it y equals c minus ax over b. Or I'm also perfectly fine with the scenario where you would happen to divide the entire side by b, which is the same thing, and do this. I'm perfectly fine with either of these scenarios because we can't reduce anything here, whereas on the problem number 13 on the left here, we could reduce those 2's for the 2L in the denominator of 2 for just that part of the fraction. Number 15 here, y equals mx plus b, and we're solving for x. So in order to solve for x, I have to undo the multiplication and addition. I undo the addition first by subtracting by b. and I ended up getting y minus b. Once again, I just went opposite order of the alphabet here this time, just put my positive one first, but feel free to have your own preference, whether you put negative b plus y or y minus b. I'm good either way. Undoing the multiplication of m by dividing by m, once again, you can do them individually or all together. I typically do it all together when there's nothing I can reduce. But when there is something I can reduce, that's when I do them individually, so I can do that reducing. Number 16, a equals p plus prt. So we have multiple p's here. That's going to come into play here in a bit. And we're supposed to solve for t. So t is being multiplied by p and r, and it's being added by p. So I'm going to do the addition first by subtracting by p. And I'm going to get a minus p equals prt. Dividing by both p and r undoes the multiplication of those, and I get t. Here, I'm going to want to do these individually, and I'll show why in just one moment. They'll both get divided by both p and r, not just one p and one r, for example. Well, a divided by p over r, I can't reduce anything there. However, this other fraction, I can reduce the p and the p. P divided by itself is 1. Anything other than 0 divided by itself is 1. So I get minus 1 over r. And so a over pr equals, or excuse me, a over pr minus 1 over r equals my t here, which once again, I want to separate them into fractions so I can reduce. When you have the opportunity to reduce, we want to take advantage of that. (17) equals 5 over 9 times the quantity of f minus 32, and we're supposed to solve for f. Okay? So when there's a fraction in front of this parentheses and we're solving for what's inside the parentheses, we could do one of two things. We could distribute this 5/9 first, or we can multiply by the reciprocal. And personally here, I'm going to choose to multiply by the reciprocal, because otherwise I'm going to get a bunch of fractions here that make this problem a lot messier than I need to. So this is actually going to help reduce the fractions, even though we'll still have fractions. So I'm going to multiply by the reciprocal, which is the same thing as dividing by the number. And we can divide to undo multiplication, which distributing is multiplication, as we touched on previously. So we multiply by 9 over 5, the 9's reduce, the 5's reduce, and you're left with f minus 32. On the other side, I multiply by 9 over 5, and I get the c over 1. I get 9c over 5, or 9 over 5c. Whether you put the c off to the side or on top of the fraction, doesn't matter. It's the same thing because this is secretly c over 1, and so they multiply 9 times c and 5 times 1. Now I'm going to go ahead and add 32 to both sides, undo the subtraction of 32 to get f by itself. And even though I have a number here, I can't combine that with 32 because one has a c and one doesn't. So I'm going to have 9 over 5c plus 32 equals f. If you put the 32 before the 9 over 5c, that's okay as well. And that's the formula to actually convert from Celsius to Fahrenheit, or it started out as up here to convert Fahrenheit to Celsius. Number 18, a equals 1/2 h times the quantity of b1 plus b2. So similar to the last problem where I undid the multiplication of the fraction first, I'm going to undo the multiplication of the fraction first here again by multiplying by the reciprocal of 2 over 1. So the 2's reduce, and on the right hand side I get h times the quantity of b1 plus b2 equals 2a, as I multiply the other side by 2, or 2 over 1 as well. Now I have to undo this multiplication of h, so I'm going to divide by h on both sides. And h reduce, and I get 2a over h equals b1 plus b2. If you distributed h, that's okay. You'll just have to undo that work later, though. Now I'm supposed to solve for b1, I should specify, b1. And so b1 is being added with b2, so I'm going to subtract b2. And I do not need to get common denominators here because these aren't things we can actually combine in the numerators. So I can just leave it like this. If this was like a b squared here, or a b2 I should say, we'd want to try and get common denominators. Or if this one was an a, we'd want to get common denominators so we could actually combine the a's perhaps. But here we don't have to worry about that. And anytime we have multiple variables here like this, we will not be worrying about getting common denominators, just to note. And so b1 is by itself, and we have our answer. I do want to note on this problem that this 1 and this 2 here are not numbers that are part of the problem as far as numbers we're working with. They're just labels for B. It refers to base 1 and base 2 in a shape. Once again, they are not numbers that we need to use to solve, so the fact that this has a 1 and this has a 2 doesn't impact how we solve it at all. It's just to differentiate or tell apart the two different bases, since both are using the letter B. It would be the same thing as having one be called B and the other one be calling F, for example, just completely different variables. Now let's use some formulas for more word problems. So sometimes solving a formula for a specific variable will help you solve the problem. And when using formulas, you might want to use what we call dimensional analysis. And that's the process of carrying units or converting units throughout a computation. So sometimes we have to convert from miles per hour to kilometers per hour, for example, or from inches to centimeters, or different conversions such as those. And while we won't be practicing those conversions here, we're going to go ahead and work on some word problems. So a car's fuel economy E in miles per gallon is given by the formula E equals m over g, where m is the number of miles driven and g is the number of gallons of fuel used. So we're supposed to solve this formula for m. So we have this formula, and we're supposed to solve it for m. And so it started off with the formula E equals m over g, and I ask, what's happening to m? The answer is it's being divided by g. How do we undo that? Well, we undo that by multiplying by g, or g over 1. And I don't know what g times e is, but I can write it down. And I know these g's reduce, so I get m. And so to solve the formula for m, we get ge equals m. So the number of gallons that are used times the fuel economy, E, in miles per gallon, gives us the total number of miles that were driven. So Claudia's car here has an average fuel consumption of 30 miles per gallon, and she used 9.5 gallons. And we want to know how far did she drive. So word problem, let's use some key information here to help us. So we don't need to know it's Claudia, and we do need to know that it has an average fuel consumption of 30 miles per gallon. We do need to know that she used 9.5 gallons, and we want to know how far did she drive. So most of the stuff is important here. Now, the average fuel consumption, that's E in miles per gallon. You see 30 miles per gallon. That's a dead giveaway that it's that. And so E equals 30 miles per gallon, or MPG. And she used 9.5 gallons. That's G per gallon. So G is equal to 9.5 gallons. And we want to know how far did she drive. AKA, we're trying to figure out what in the world is M. M equals question mark. That's what we want to know. And so we're going to take this equation. We can either take this original equation or the one we already modified to solve for N, which is why it asked us to do that in part A, and plug in E and G. So I'm going to take GE equals M, that equation we solved for M already up above, and I'm going to plug in G as 9.5 and E as 30. So I'm going to have 9.5 times 30, and that'll equal M. And we're going to figure out how far Claudia drove on 9.5 gallons of gas, given that she gets the gas mileage of 30 miles per gallon. So 9.5 times 30 is 285. So 285 equals M. So Claudia drove 285 miles. Now, this is actually something that is very practical. It's something that my wife and I use when we budget for trips where we're going to be driving. So for example, what we do is we say, we type into Google Maps or any maps site and say, from our starting location, our home, to wherever we're going. So a couple summers ago, we went to Branson with my wife's family. So we went from, where we're at in Omaha, or we were in Plattsmouth at the time living there. Now we live up in Bellevue, but we were saying where we're at in Plattsmouth, traveling to Branson, it's whatever number of miles it told us. And we said, okay, based on that many miles and our car's current miles per gallon, we were able to figure out how many gallons of fuel we would use approximately. And it's not a perfect science, but it's a really good estimation is what it is. And so because we were able to figure out how much gas we would end up needing for this trip to get there, get back, and maybe a little bit of driving around while we're there, we were able to then say, okay, we're going to need this number of gallons. We know gas costs about this much, whatever the price was at the time as it fluctuates. And so based on that, we were able to say, okay, this is how much money we're going to have to spend on gas on this trip. And that allowed us to budget properly for this trip and make sure we had enough money, and we didn't go in and be like, oh crap, we spent so much money on gas, we weren't prepared for that, and now, what do we do? So instead, we were able to set aside the money ahead of time, so that way we would have good expectations on how much we'd have to pay for gas, and we weren't surprised at all when we end up, totaling up the gas at the end, or paying for gas at the pump each time down the road. So this formula for the volume of a cylinder on number 2 is V equals pi r squared h. And that's just the formula. I said this formula. Where r is the radius of the cylinder and h is the height. And we're supposed to solve this formula for h. So we're going to take this formula and solve for h. So V equals pi r squared h. And to solve for h, we say h is being multiplied by pi r squared. So we're going to divide by pi r squared. And we do it to both sides. On the left-hand side, I don't know what V divided by pi r squared is, but I can write it. On the right-hand side, pi divided by itself is 1, r squared divided by itself is 1, anything other than 0 divided by itself is always 1. And we just get h. And so we successfully solved for h like it asked us to. Next, what is the height of a cylindrical swimming pool that has a radius of 12 feet and a volume of 1,810 feet? Now, I'll go and spoil and say everything is key here for key information. So let's go ahead and work on our on what part is what. So what is the height? That's a question we're trying to find. We're trying to figure out what is h. So h is question mark. We don't know yet. We know it's a cylindrical swimming pool, and it has a radius of 12 feet. So r equals 12 feet. And a volume of 1,810 cubic feet. So volume of 1,810 cubic feet. Even though we say the word cubic first, the cube symbol goes at the end of feet. And now what we can do is we have h, r, and v assigned, where h we don't know, and we can plug them in up here. We don't need to know the value of pi because we are just going to use the approximate of 3.14 when we get into the computation. And so v over pi r squared equals h, plug in r and v, and we'll end up getting 1,810 over pi times 12 squared, or r squared, equals h. So here, I go ahead and do 12 squared, and I end up getting 1,810 over, I'm going to switch the order of these two as well, so I put the irregular number first before pi, 144 pi equals h. And I'm going to go ahead and let my calculator do the work here, as I would type in 1,810 divided by 144 pi, and you can just use the pi button on your calculator actually. And the calculator's in my room. We have to push one of the other buttons, the second button or the alpha button, in order to get to pi. It ended up being second, and then the caret, which is right above division symbol, so it's a little blue symbol on the calculator right above the division symbol. So you put second and then that little up arrow caret looking thing. It's called a caret for English. And so you have 1,810 divided by 144 pi. If you can't find the pi button or your calculator doesn't have it, you could always substitute 3.14 as an approximation. And we're going to round here to the nearest whole foot. And so we're going to get h is approximately, I'm going to use this little symbol there for approximately instead of equals. Equals is straight lines, approximately are these little curves, wiggly lines. And so it's close to 4 feet. So the swimming pool is approximately 4 feet tall. Not exactly 4 foot, but very close. And that closes up this unit and this section of Algebra 1.